the last translation that we need to explore is that of vertical stretching and vertical compressing. Now, as always, let's begin by supposing that we are given a function y equals f of x, our parent function or basic graph. Now here, we say that for some positive constant a, the graph of y is equal to a multiplied by the parent function can be obtained one of two ways. So we can say that the graph of y is equal to our constant a times our parent function can be obtained by vertically stretching the graph of the parent function if we have that the absolute value of our constant a is greater than 1. Or we can say that this graph a times the parent function can be obtained by vertically compressing the graph of our parent function if the absolute value of our constant a is strictly greater than 0, but strictly less than 1. So in this first case, when we say that we are vertically stretching the graph of our parent function, this implies that the y values of our new function are growing a times as fast. Now, when we talk about the parent function being vertically compressed by a factor of a, this means that the y values of our new function are growing a times as slow as the y values of the parent function. Now, observe here, in both forms of our definition, we have these absolute value bars around our constant a. What does that imply? Well, we want to think back to our last translation, reflections. And we'll note here that if the constant a is less than 0, this is implying that we are also incorporating a reflection as well as a stretch or compression. So this is a reminder to be mindful when you're looking at those constants multiplying a parent function. Now, to better appreciate these vertical stretching and compressing of a graph, let's consider the following example. So here we are asked to graph the functions g of x is equal to 1/2 times x squared and h of x is equal to 3 times x squared. And as always, before we get started on sketching these graphs, let's begin by identifying the parent function for g and h, and then describing the individual translations needed to obtain those functions. And looking at both of our given functions here, we can see that the parent function is the squaring function. Now, since we are considering vertical stretching and compressing, we want to make note of these ordered pairs since we'll be manipulating their y coordinates to produce the functions for g and h. So looking at our graph here, we can see that we have 3 focal points that we want to keep in mind. We have the ordered pair -1, +1, the origin 0, 0, and our third point, +1, +1. So now that we've identified our parent function, let's consider both of our given functions. So starting with g of x, so looking at our function g of x, we can observe that the constant that's multiplying the squaring function is 1/2. And we can also see here that the absolute value of 1/2 is going to be strictly greater than 0. But since it's a fraction, it's also going to be strictly less than 1. So with this condition, we know that this means or tells us that our function g of x, which is 1/2 times x squared, vertically compresses the parent function by a factor of 1/2. Now, to obtain the y coordinates for our function g of x, we simply need to take the parent function's y coordinates and multiply them by this factor of 1/2. Producing these solution points, -1, +1/2, the origin will stay the same since 0 times anything is 0. And the third ordered pair, +1, +1/2. So plotting these 3 new solution points on our graph, the origin will remain the same. Now here we have when x is -1, y is going to be positive 1/2. And very similarly, when x is positive 1, y is also 1/2. So notice here how our y values are growing half as fast as the parent function. Now what about our next function, h of x? So looking at h of x, we can see we have a constant 3. So with this, we can say that a in this case is equal to positive 3. And since we know that the absolute value of 3 is going to be greater than 1, this is telling us that our function h of x, which is equal to 3 times x squared, vertically stretches the graph of the parent function by a factor of 3. And again, in order to sketch a nice accurate graph here, we want to consider multiplying the y-coordinates of our parent function by this factor of 3, producing 3 new solution points, -1, positive 3. Now again, our vertex or origin here is going to remain as it is, 0, 0. And then last but not least, we have the third ordered pair, +1, positive 3. So again, the origin remains as it is, but now we have that when x is -1, y is up here at positive 3. And very similarly, when x is +1, again, we have the corresponding y value for this point is positive 3. So notice in this case, as we connect these 3 points with a smooth curve, we can see that the y values, our graph has gotten more narrow. The y values are going 3 times as fast as our parent function's y values.